Hi everyone, welcome back. Now we're moving on to question 17, which is actually an extension from question 16 that we did previously. The question reads, would the answer to the previous question, namely the amount of time to return to the starting position, be the same for a uniform disk with the same coefficient of friction launched to the same initial conditions? So let's think about what this means. If it was a uniform disk instead of a hoop, then the moment of inertia would definitely be different. The moment of inertia of a disk is equal to 1/2 mr squared, whereas the moment of inertia of a hoop is just mr squared. So it's twice, it's half of the moment of inertia of a hoop. Um, let's plug. So here's all the calculations from last time. Let's see what happens when we plug in this moment of inertia to the equations instead of the hoop moment of inertia. Okay. So let's begin with moving to the right. So this is initially when it is first placed on the ground. The hoop is spinning counterclockwise, whereas the hoop is moving to the right. So these equations still stand. The only difference is that right here in the place where we have angular acceleration, we will have 1/2 mr squared, or sorry, 1/2 mr in the 1/2 mr squared in the bottom, and then when you simplify it down, the 1/2 moves to the numerator, so then it will be 2 times the force. Here, let me actually just make a copy of everything so I don't lose this word. Actually, it's fine. Yeah, it's 2 times. 2 times what was originally there. And what this means is that right here there's also a 2 in front. So basically the angular velocity is slowing down a lot faster than it was previously. So right here it would be minus 2 v naught plus 3 v naught over r. So then actually the angular velocity final is going to be v naught over r rather than 2 v naught over r. These other things are not affected. The net force and the acceleration and the delta x and the time it takes for it to get to the place where v final is equal to 0, all this stuff is not affected. So what is affected though is that after it stops moving translationally, the angular velocity that we're left with is v naught over r rather than 2 v naught over r. Now remember what we were saying about how this equation, once this equation starts to hold, then the velocity of the center of mass does not move any faster, and the angular velocity doesn't change. It's in it's in equilibrium when this equation holds. As you can see, since the angular velocity starts at a much smaller value than previously, it makes sense that it will have a different outcome because it will actually reach this condition where the velocity of center mass and the angular velocity doesn't change anymore. Let's just prove that quantitatively though. So again, these two equations still hold right here, and this still holds. The only thing, hold on, so this thing we have to be careful. Remember in a past video, we had to make sure that the time that it takes for it to get back right here, it had to not follow this condition. If it had to follow this condition, then it wouldn't be this time because it wouldn't be accelerating anymore. It would be with a constant velocity. But let's actually see if this condition is starting to hold at all. And how we see is we know that the velocity of the center of mass, the equation for the velocity of the center of mass is acceleration times time. And then the equation for, so circle this guy, the equation for the angular velocity is negative f. So again, there's a 2 here now because we have a different moment of inertia. So this is the equation for the angular angular velocity. So if we multiply by this, so let's plug in both of these to this equation. So we get AT is equal to, okay, and then plug this guy in. So negative 2f over mrt plus the initial or the final after it stopped moving. So that's v naught over r. So this is the condition that holds. And now we have to see exactly what time does it happen. And the time is going to be, we can calculate it. So hold on, let's plug in acceleration. What is acceleration? Acceleration is F over m. So let's change this to F over m. And then I'm going to add it to both sides. Oh, this is a bit messy. Hopefully you guys can follow along still. I'm gonna continue my work right here. We have 2f over m r t plus f over m t is equal to v naught over r. So what we're trying to do right now is we're trying to find t and see if t is less than this t right here, the time that it would have taken for it to go all the way back to the original position. If it is less, that means that it actually reaches this condition where it stops moving, or where it stops changing the velocity of center mass and the angular velocity before it reaches the end. So we will have to do it a different way then. Let's see. So this thing simplifies to f over m t times 2 over m plus 1, right? So v naught over r. And then we can simplify this a bit further. This is going to be 2 plus m over m times f over m squared root of v naught over r. So, actually pause real quick. I think I made a little mistake right here. When I first made this equation where I plugged in velocity of center of mass, when I first plugged in the velocity of center of mass and plugged in the omega using this equation and this equation, I plugged it in, but I forgot to multiply this by r, right? Because there's an r in this equation. So actually, the answer is a bit different because there's no r here, and there's no r here. There's no r here. There's no r here. So this actually, hold on, let me just redo this part. Sorry about that. Let's get rid of this place. So this will be 3f over mt is equal to v naught, right? So t is equal to m v naught over 3f. Now this actually is smaller than the time, right? This is 1 over 3 times smaller than this guy right here, which tells us that it actually reaches this condition where it starts rolling without slipping before it gets to the very end. Okay, and what that means is that instead of the v center of mass continuously increasing, the velocity of the center of mass is going to stay constant. And it's going to stay constant at a times t, where t is this time that it takes for it to get to the condition of rolling without slipping. And then the time that it takes for it to get back to the original position is going to be dependent on how much time it takes for it to go at a constant velocity now. We could go ahead and calculate exactly how much time it would take, but we don't need to because the question actually doesn't require you to know exactly how much time, but just is asking would it be the same. So the answer obviously is not that it will be the same because it stops accelerating. So the torque due to friction is larger for the hoop? No, it's not, because it says let's see. With the same coefficient of friction and launched with the same initial conditions, so it's not like it's getting more mass, so the friction is the same. No, because the disc never returns to starting position. No, it does return to the starting position because remember, it just starts rolling at constant velocity v center mass. No, because it just stops slipping too soon, and that's the right answer because it stops slipping sooner, and then it just starts rolling without slipping at a constant velocity.